please, please.
How you can define subgradient of multivariable functions? For example, how to calculate subgradient of mod x plus 1?
Subgradient of
More than one variable.
more than one variable. Well, the definition I gave it is for several variables. In the particular case that you are telling me, this is the question. Okay, you can apply the definition of subgradient, and there is no problem. In fact, except at points where the sum is 0, the function is differentiable, and then this gradient is just a gradient. Okay, but at the points where this yeah, on that line, the function would not be differentiable, but still you can apply the definition and you will get this. The condition is x plus y greater than or equal to, at a point where the sum is 0, greater than or equal to 0 times x star x plus y star y for every xy. That's the condition. Okay, and then you can solve this system. You can also apply composition rules. There are other ways. Do you have an explicit formula for this particular case? I mean, it's not difficult. Usually we deal with
one variable function like the model.
if you want a clear example in more than one variable which generalizes the mod case, consider the norm. It can be seen that outside the origin it's differentiable, and then, as we are going to see, the subdifferential coincides with the singleton of the gradient. But what happens at the origin? What's the condition to be a subgradient? Okay, then if you write the condition, it would be norm of x greater than or equal to the norm of 0, which is 0, plus x star x minus 0 for every x. Which are the vectors x star that satisfy this condition? Exactly those which have norm less than or equal to 1. I mean, first of all, this condition says nothing if x is 0. So consider x different from 0. Then you can write this as x star x divided by the norm of x less than or equal to 1 for every x, means for every vector of norm 1. And the maximum of these expressions over vectors of norm 1 is the norm of x star. So this is norm of x star less than or equal to 1. In the opposite direction, this is satisfied if the norm of x star is less than or equal to 1 by Cauchy-Schwarz inequality. So the conclusion is that the subdifferential of the norm at the origin is the unit ball, of which the case I mentioned this morning is a particular case, because for one variable, the unit ball is the interval minus 1, 1. Okay? Well, it's okay. So any other question about what what we have seen so far. Okay, this morning I finished having troubles which were not real troubles. So let me repeat what we were doing. We are considering a convex function on the interior, a point on the interior of the domain. Then we set the directional derivative, one-sided directional derivative is the limit as t goes to 0 plus f of x plus td minus f of x divided by t. And I said, but does this limit exist? And I said, yes, it exists, at least in the extended reals, because this expression is non-decreasing in t, so the limit is actually the infimum over t positive of the same expression. And the infimum always exists in the extended reals, but it might be minus infinity, a situation that we wouldn't like. But it is not minus infinity. And then I was having troubles. I thought I was having troubles, but it was not the case, to prove that this expression is bounded from below. And then the infimum is finite, it's not minus infinity. Then what I was trying to use, or to prove, is the fact that for every t positive, this expression is greater than or equal to f of x minus epsilon d divided by epsilon, when epsilon is small enough so that x minus epsilon d is still in the domain of f, so that this value is finite. Okay? Such epsilon exists because x is in the interior of the domain. And then I was manipulating this expression. I said epsilon over t So if I am not wrong, I arrived at this expression, which I didn't like. I said, I don't like the signs, there must be a sign mistake. Why didn't I like? And there is no sign mistake. And this is completely useful for our purposes, because now you can write 1 plus epsilon t f of x less than or equal to f of epsilon minus x minus epsilon d plus epsilon over t f of x plus td. This is what we want to prove, okay? I'm trying to prove this inequality. These are equivalent inequalities. And then solving for f of x, this gives us f of x less than or equal to t plus epsilon divided by t, f of x minus epsilon d, plus epsilon over t plus epsilon. Is this correct? No. Yes. Then again, I'm having troubles.
Sir, first constant.
Sorry?
T upon T plus epsilon.
Here it's wrong. T over T plus epsilon. And why is this true? This is true because X is T over T plus epsilon, X minus epsilon D, plus epsilon over T plus D, X plus TD. Is this true? We can check. X, the factor is T over T plus epsilon over T plus epsilon, which is equal to 1, so it is X. And the term in D vanishes, because the coefficient is minus epsilon T over T plus epsilon, plus the same, epsilon T over T plus epsilon. So this equality is true. So, and these coefficients, T over T plus epsilon and epsilon over T plus epsilon, are non-negative, because both T and epsilon are non-negative, and their sum is equal to 1. So what I have here is f of a convex combination. By convexity, this is less than or equal to the corresponding convex combination of the values. So this is true. So I can remove now the question mark here and conclude that this is finite. This is actually greater than or equal to this. This is an upper bound, a lower bound, and this is the largest lower bound. Okay. So the conclusion is, on the interior of the domain, all the one-sided derivatives exist at every point and every direction, and they are finite. Is this clear? Then, what's the relation between subgradients and directional derivatives? Before answering that question, let me tell you something which will be required. When I defined the subdifferential, I insisted that I can define it for an arbitrary function, non-convex, no problem, although in such a case it would be often empty. But I can define it anyway. And I recall the definition. Written in a slightly different equivalent way. Okay. So I said this expression, this subgradient inequality, says that the subdifferential is the solution set of a linear inequality system. On X star, this is a linear inequality. We have infinitely many. So we have the solution set of an infinite linear inequality system, which is a closed convex set. This is convex and closed. But now, when we are at a point belonging to the interior of the domain, I can say more and can say that this set is not only closed, but compact. So it's also bounded. Why? Because Consider the unit vectors. The 1 is in position I. Because x bar is in the interior of the domain, if I move a little bit along any of these directions, I stay in the set. This means for epsilon positive small enough, x bar plus minus in both cases, I move in both senses, epsilon I would still belong to the domain of F, okay, because of the interiority assumption. And then, what do we have? Apply this inequality first for x equal x bar plus epsilon I, and then for x bar minus epsilon I. Then what we get is, in the plus case, epsilon comes out, and then EI times the difference is the ith component of this difference, okay? So, so x is here. So what I get is the ith component of x star. So I get that x star I, the ith component of x star, is less than or equal to f of x bar plus epsilon EI minus f of x bar, which is a finite number because x bar plus epsilon I is in the domain of the function. Then when I apply it to x bar minus epsilon I, what I get is minus epsilon x star I less than or equal to f of x bar minus epsilon EI minus f of x bar. So, in conclusion, x star I is between f of x bar minus f of x bar minus epsilon EI divided by epsilon and f of x bar plus epsilon EI minus f of x bar divided by epsilon, if I am not wrong. Is this correct? So each component of x star is bounded from below and from above. So x star is in a bounded set. Okay? So this closed convex set is not only closed but compact. But I insist, when x bar belongs to the interior of the domain of F. This is no longer the case when x is not in the interior of the domain. Consider, for instance, this function. Just a very simple example. F of x equal x if x is non-negative, plus infinity if x is positive. Okay, this function has this graph. On the right, it's plus infinity. So the epigraph is this set, which is clearly a closed convex set. So this function is convex and lower semi-continuous. But what is the subdifferential of this function at the origin? This is the set of slopes of straight lines through the origin that are below the graph of the function. And because there is no point in the graph of the function on the right, then every right, every straight line with a slope greater than 1 is a subgradient. I mean, every number between 1 and plus infinity is a subgradient. So we have here that the subdifferential is a half line, so it is unbounded. This situation is possible because this is a boundary point of the effective domain of the function. Such a situation would be impossible, as proved here, if we were on the interior of the domain. Is this clear? Now, I go back to the question I made a few minutes ago. What's the relation between subgradients and directional derivatives? Let T positive. I mean, I insist that we are on the interior of the domain. And then I consider T positive, and I consider as subgradient. Okay? Then, I will write the subgradient inequality for x bar plus TD. This is greater than or equal to f of x bar plus x start product the difference between these two, which is T times D. This means that f of x bar plus TD minus f of x bar plus T is greater than or equal to x star D. By the way, this should be an alternative way of proving that this infimum is finite, after we have proved the existence of a subgradient on the interior of the domain, which we did this morning. Okay, so now you have two proofs of the same fact. Well, then the infimum here, or the limit as you want, which is the directional derivative, satisfies this assumption, this inequality. And this is true for every x star in the subdifferential. So I can write that f prime of xd is greater than or equal to the maximum over x star in the subdifferential of x star d. I have the right to put maximum here because we already know that this is a compact set. So a linear function, this is linear as a function of x star, attains a maximum at this compact set. Okay? But I'm going to prove that the equality holds. And yesterday I was thinking, well, I want to prove this, but how can I? I mean, the classical book where you would look at for such proofs would be Rockefeller's book, of course. Classical book. You probably know Ralph Tyrrell Rockefeller. Convex analysis. Analysis, 1970, the first edition. There have been other editions, Princeton University Press. This book has a problem. What's the problem? That is perfect. It's perfectly structured. So when you look for the proof of a result, which is in chapter 10, that proof relies on results for the previous 9 chapters. So you don't have an independent proof. It's very good because it relates all the results. It shows the relationship between all the results, but it's not helpful to me if I want to give a proof. I cannot tell you all Rockefeller's book just to prove this one. And then in particular here I need to discuss about support functions of closed convex sets, the so-called Hormander duality between closed convex sets and sublinear functions, etc. And I wanted to avoid all this. And I said, can I give a very short proof of this? Then I found one, which I think is correct and very short, and that you, Vivek, will particularly like, because I'm not going to use this term, but you will see tangential subdifferentials, which you are very familiar with and you like a lot. So the proof I discovered yesterday I discovered the proof. Now I will discover that it was wrong, but okay, these are the risks of doing new things. Consider this function. I mean, we are fixing x bar, and I look at this function as a function of the direction. It's very easy to see using the definition of the directional derivative that this function is convex as a function of d. Well, just look at this expression. This is clearly convex as a function of d, and then we take the limit, so it's convex. And it's convex, and as we have seen, actually twice, is finite value, because this infimum is finite. So it's finite everywhere. Everywhere. Then let's look at a particular d. This d belongs to the interior of the effective domain of this function, because the effective domain is the whole of Rn. So the interior is the whole of Rn. And we have proved that a convex function has a subgradient, has a non-empty subdifferential at every interior point of its domain. Okay, so this means that the subdifferential of this function at this particularly d, actually at every d, is non-empty. Since it is non-empty, I take a point in it. So you are seeing here the tangential subdifferential, okay? But this is just between you and me. Then what happens? Let's write the subgradient inequality for this particular subgradient. So this function, okay, if you allow me to change a little bit the notation, I consider d bar instead of d. And now the subgradient inequality would tell us that f x bar d is greater than or equal to f prime x bar d bar plus x star d minus d bar for every d in Rn. Do you agree? If you agree that this is true for every d in Rn, I apply this to twice d bar. And remember that directional derivatives are positively homogeneous in the direction. If I multiply the direction with lambda, I can write here I get t lambda, then I can put here t lambda and then plus lambda as a factor here, and it comes out. It's a very easy trick. So lambda comes out, it's positively homogeneous. So this means that twice f prime of x bar d, because the two came out, d bar, is greater than or equal to f prime of x bar d bar plus x star d bar. Okay? Moving this to the left-hand side, I am left with this inequality. Do you agree? But then I repeat the game, but now with d equals 0. Why not? Now I was about to do it for d equal 1/2 d bar, but no need. For d equals 0. For d equals 0, the directional derivative is clearly 0. If d is 0, then you get 0. So you get 0 greater than or equal to f prime of x bar d. D is 0 minus x star d bar. So we get x star d bar greater than or equal to f prime x bar d bar. And we already have the opposite inequality. So we have equality. And this is the end of the proof. Because I have proved that for a particular x star, this expression coincides with f prime of xd. Okay, so at the maximum, we get f prime of xd. Do you agree with this proof? Do you agree, Vivek? So it's very, I was surprised to find this proof. So what's here? For sure. Yeah, I always forget bars and such things. Yeah, thank you. Yeah, I'm coming from here. So left-hand side is 0. And second, I don't touch anything here. And here I make d equals 0. So I get minus x star d bar. So this is a very important property which holds in the interior of the domain of a convex function. No, but these notions yes, this has very important consequences. This has very important consequences. Recall that this is for F convex. Again, one bar is missing. And X bar in the interior of the domain. And D is any direction. Okay? That's the setting. So now, again, assume C is an open convex set. And F is a real valued function on R, or simply you take C equal Rn. No problem, because then I'm going to play only on the interior of the domain. Suppose this function is convex. And take a point X bar in the interior of the domain of this function. Hello. Then F is differentiable at X bar if and only if the subdifferential has just one element, is a singleton. And in such a case, this is the subdifferential, this is the singleton of the gradient. Okay? Implication from right to left. Suppose the subdifferential is a singleton, it has just one element. Then use this expression. You have that for every D, F prime of X bar D is equal to X star D. There is only one. The maximum is attained at the only existing element in the set. This is telling us that the directional derivative as a function of the direction is linear. The function is so-called Gateau differentiable. If you admit Gateau differentiability as your notion of differentiability, this is the end of this implication, of the proof of this implication. If you don't like it because you prefer Fréchet derivatives, no? Or Fréchet differentiability, then simply use a fact I'm not going to prove, but you can find in Rockefeller book, which says that for convex function, Gateau and Fréchet differentiability are equivalent. I mean, for arbitrary functions, Fréchet implies Gateau. A Fréchet differentiable function in the ordinary sense is Gateau differentiable, means the directional derivative is linear. Okay? But for convex functions, the converse also holds true. If you have a Gateau differentiable convex functions, it is differentiable in the ordinary sense, in the Fréchet sense. Okay. But now let us make the proof in the opposite direction. Suppose f is differentiable at x bar. I want to prove that the subdifferential has only one element. By the way, here we have proved not only the implication from line to left, but also this equality, because the directional derivative is the gradient inner product the direction. So these two linear functions coincide. This implies that the vectors defining these linear functions are the same. So this shows that x star is the gradient of f of x bar. X star was the only element in the subdifferential, so the subdifferential is the gradient. But in fact, this equality, which is already proved, but we are going to prove it again. As a consequence of this implication, which I'm going to prove next. This was what we already proved, so we are now proving from left to right. Okay? So now we are assuming that f is differentiable at x bar, and so let us prove that there is only one element in the subdifferential. Take one element. We know that this is non-empty, but it may have infinitely many elements. Take one, and then because of this inequality, for every d, for every direction d, we have x star d less than or equal to f prime of x bar d. Okay? But we are now assuming differentiability. Frechet differentiability, which implies Gateau differentiability, which means that this directional derivative is simply the gradient times d. And this is true for every d. So we have two linear functions, functions of d, x star d and the gradient times d. And one is everywhere smaller than or equal to the other. Then they must be the same. Here you have x star minus the gradient of x bar times d less than or equal to 0 for every d. If this is true for every d, in particular, this is true for x star minus the gradient of f of x bar. I can put any vector here. And then I am getting the norm of x star minus the gradient of f of x bar to the square less than or equal to 0, which implies that x star is the gradient. So this proves the implication from left to right, but again this equality. I have taken an arbitrary element, an arbitrary subgradient, and proved that it is the gradient. So there is only one, the gradient. It's a singleton. Okay? Well, so this notion of subdifferential is very good, very nice, very natural, and very appropriate for dealing with convex functions, but it could be useless. It would be useless if it wouldn't enjoy nice calculus rules. But it does. Okay, we are going to see additivity. Well, there are some simple properties which are elementary exercises, If you multiply the function with a positive lambda, then this lambda comes out. This is trivial. But now we are going to see additivity, which is not trivial. And in fact, it's not always true. Okay? But it's very often true. So suppose you have two functions, fg, and a point x bar, where both functions are finite. So belonging to both domains. And then I can consider the subdifferential of f, the subdifferential of g, and the subdifferential of f plus g, always at the point x bar. Okay? Because x bar will also belong to the domain of the sum, which is the intersection of the domains. Then the sum of the subdifferentials is contained in the subdifferential of the sum. Did I forget anything? Did I forget to say that the functions are convex? No, I didn't. This is true for every function. This is a trivial result. And if you take x star here and y star there, then, and you take then any x in Rn, then because x star is in the subdifferential of f of x, you have f of x greater than or equal to f of x star plus x star x minus x bar. And similarly, you have g of x greater than or equal to g of x star of x bar. Sorry. I have a tendency to interchange freely bars and stars. I should avoid that. And now I am also interchanging x with y without any reason. Okay. And now if you add these two inequalities, then you get this greater than to or equal to f of g, f plus g of x bar plus x star plus y star x minus x bar. So it's a very, very elementary exercise. So this inequality, because it holds for every x, is telling us that x star plus y star belongs here, so this inclusion is true. What about the opposite inclusion? Is it true? Often, but not always. Notice that the opposite inclusion cannot be so simple, because we have to prove that every element here can be decomposed as a sum of one element in the subdifferential of f and an element in the subdifferential of g. We have to find a decomposition. This is not such a simple algebraic exercise as here. We have to find the decomposition. And this decomposition does not always exist. But it exists when X does not only belong to the intersection of the domains, but also to the interior of the domains. By the way, I said that I would not talk too much about supergradients, but at least a little bit. Subgradient inequality would be this one with less than or equal to. I mean, we have to change signs always. I will not talk more about that. Okay. Yes. Of course. No, I have not chosen anything. No, I have not chosen X bar. One thing is to say, let X bar belong, or let X star belong to there, and another thing is saying, take X star from there. When I take, I am choosing. Now when I say, let X bar be, I'm saying, if there is some X bar there, with that X bar, I do whatever. It may not exist. I mean, writing that star, I'm saying if there is an X star there and there is Y star there, the sum satisfies this and that. I'm not assuming non-emptiness. But in fact, if this is empty, then the sum is empty. So the inclusion holds anyway. Now this is an interesting comment. But, okay. So now, suppose X bar belongs to the interior of the two domains. To the interior of the intersection of the intersection of the interiors. That's the same. Then, we have equality. Okay, let's see that. So one inclusion is proved. Now we are proving the opposite inclusion. So let X star be an element in the right-hand side. If you are worried about this, again, if the right-hand side is empty, the inclusion is automatically satisfied, okay? But let X star be an element here, and we have to find out the composition of X star as the sum of an element in the subdifferential of F at X bar plus an element in the subdifferential of G at X bar. How can we find such a decomposition? Let us write the subgradient inequality. For every X in the space, F plus G X is greater than or equal to F plus G of X bar plus X star x minus x bar. Just the separating inequality. But I'm going to express it in a different form. F of x minus x star x is not here, it's there. Yeah. Is greater than or equal to minus g of x plus f of x bar plus g of x bar minus x star x bar. Well, this is correct. In fact, I could have moved x star x in the right-hand side. This does not change anything. But I was checking what I had in the notes. In case I get into troubles, I have something to compare. Okay, so then I put x star x on the left, although it could be on the right. Then what do you see here? Observe that this inequality is satisfied for every x in the space. So what do we have on the left-hand side? Convex minus linear, this is convex. What do we have on the right-hand side? Concave, because G is convex, plus constant, so concave. Convex greater than or equal to concave. What happens in this situation? There is the so-called sandwich theorem, which is not true in the way I'm going to state it, which says that if you have a convex function and a concave function below it, there is an intermediate affine function. This is almost immediate. This is wrong in the way I stated it. Okay? And I will give a counterexample. But after giving the correct assumption, it will be true, and this is obtained by separating the epigraph with the hypograph. You find a separating hyperplane, and this separating hyperplane defines an affine function which is below the convex function and above the concave function. This is almost always true, but not always. Can you give me a counterexample? I'm going to make you a very simple question for which you are likely to give me a wrong answer. Consider these two functions. Square root of x, of course for x non-negative, and minus the square root of minus x for x negative. Okay? Which function is above the other? Which is larger? The first or the second? I told you that you will give me a wrong answer. You are warned. Well, that's the point. That's the point. The domain is different, but a very quick and very wrong answer is, of course, obviously positive is greater than negative. That's it. But of course, the domain plays some role. So, in fact, this function is concave, and this function is convex. And we are all the time, when dealing with convex functions, assuming that outside the domain is plus infinity. So this function is plus infinity if x is positive. And this function, we are changing signs when moving from convexity to concavity. This function is minus infinity if x is negative. So the graphs are for the convex function, this is the function here and plus infinity on the right. For the concave function, this is the graph here with minus infinity of the right. In fact, the only point in both domains is this one where you have equality. But when I compare both functions as functions on the whole of Rn, this one is below. Is below. No, this one is below. On the left, the convex, this one, is greater than minus infinity. And on the right, the convex is plus infinity, so greater than this. So both on the left and on the right, the convex is higher. So this function is larger at every point. Almost always we are comparing plus infinity or minus infinity with a number, except at the origin where the two functions coincide. But then, of course, so if you call this, I don't know, f, and you call this h, f is convex, h is concave, then f is greater than or equal to h everywhere, but you cannot find an affine function between the two. Because now if you separate this epigraph from this hypograph, I mean here the slope is plus infinity in both cases, then the only separating hyperplane is vertical. So it does not define, it's not the graph of any affine function. There is no intermediate affine function in this case. Okay? But so this possibility has to be excluded, and it's excluded because x bar belongs to the interior of both domains. Notice that 0 was now in the boundary. So this situation is not possible in our case. Then, I don't know how much time do I have? Then it's better to postpone this proof to the next class? Okay. Then, so only this proof is, it will, I don't know how long it will take, maybe we'll raise some discussion. So maybe it's better to postpone it, and then only this is left. And another thing which I included in the last minute, I decided to include it this morning, which is something which to me is very fascinating. Not the result itself is, but what is fascinating is the proof, not the classical proof, not my proof, but a proof I learned about the following fact, about integration of subdifferentials. Consider gradients. If you have two functions on an open set with the same gradient everywhere, then the two functions are the same up to a constant. Okay? I mean, the derivative everywhere. I mean, if two functions have the same derivative, then the difference is constant. Then, if two convex functions have the same subdifferential everywhere on a convex open set, they are the same up to an additive constant. Find this result in Rockefeller book and look at the proof. Any? Hmm? An additive constant. So if an additive constant. So the proof in Rockefeller's book is very discouraging. I mean, you have to, as I said, to look at many results, previous results, some of them non-trivial, etc. Tomorrow, I will give you a very simple proof, algebraic proof, that you will never forget, that you can improvise at every time. So this morning I was thinking and I said, oh, maybe I should include this result, but would I be able to improvise a proof? And yes, I did, immediately. And then after I tell you the proof, you will be able to reproduce it at every time. Okay? So these are the only two things missing in this. I will tell you about who produced this proof and some, I mean, an anecdote related to this. And then after finishing with these supergradients or subgradients, then we will go back to economics, because if you remember well, we were dealing with cost functions and production functions. Okay? But now it's better to stop, probably.
So we can have tea outside and then after 5 minutes we proceed.
So in the result, if the derivatives are equal, then their difference is constant, and here is also the difference is constant, right?
Yes, but these are one-sided directional derivatives.